if you want to solve an optimization problem, you have to minimize a function, say over Rn, just or R, whatever you want, doesn't matter. Unconstant problem, a nonlinear problem, differentiable of course. So what should you do? Well, what is the basic philosophy of minimizing a function? What is the maybe you don't want to solve even grad f x not equal to 0, or it's very difficult to solve it. So, or what would you do? See, optimization algorithm actually, algorithms run on this very fundamental fact that you choose a starting solution. So, then check with an optimality condition. And if it is a solution, then it must satisfy this. Does it do so? If yes, then stop. But that doesn't mean that it is a solution. I am happy just with that, a critical point. And if not, so if yes, then stop. So the flow chart is like this, and if no, if it is no, then you go from xk to xk plus 1. That is, I am assuming that you already in the kth stage, so you go from x0 to x1 such that f of x1 is strictly less than f of x0. So this approach is called the descent method. You are always trying to go make the function value go down. So this is what you have to do. So you start with a starting solution. If it is a solution, stop. If it satisfies the optimality condition, stop. If not, try for by some method another solution where the function value is going down, slower. So this is the whole thing. Now how would you do that efficiently gives rise to this whole subject of algorithms in optimization. And that gives the subject its many flavors actually, it has many way of looking at it. And so what one does, there is something called now, how do I know given a point x bar, say xk, and I know that this is not a solution. So now are you going to really check grad f x k not equal to 0? You might not get any point for which grad f x k is equal to 0, because there are a lot of errors which creep in when you do this computation. So what people usually do, people put in a tolerance, epsilon greater than 0, there is a tolerance level. So when you put in a tolerance level, you say that okay, I will stop if I have, so if I xk is not this, but the norm of the vector, that is the distance of this vector grad f x k from 0 is strictly less than epsilon. If I find like this, where epsilon is a very small number, very, very small, almost 0. So if it is just less than that, that will do for me. I need not bother about f x k equal to 0. So the solution you get is some kind of approximation. So that is why there is a lot of analysis of approximate solutions in optimization research. And so this tolerance, so how do you choose a tolerance is the issue of the people who are implementing, right? And now here we are going to explain to you what are the basics of a descent method. So given a point xk which is not a solution, in which direction I should move so that I get a new point at which the function value is strictly lower than the current value. Then I am minimizing, I am making the function value go down. So that's the key. So how do you do that? So, the key idea is to find a D. Find a D greater than D element of Rn and lambda greater than 0 such that f of xk plus lambda D is strictly less than fxk. That is my, so my new value is this. So I have to find some lambda k if you want to write it like this, because lambda k will change from k to k. So this is what I want. So xk plus lambda k d is my xk plus 1, the next point. So what should be the choice of d so that this happens? So one choice, a very important choice, see, is the negative of the gradient itself. So let me tell you why, how can I get this? Because it is differentiable. Suppose I have that, I choose a d, is strictly less than 0. Strictly less than 0. So if that happens, if I write down the definition of the derivative, because it is differentiable, so as I told you, if when a function is differentiable from vector calculus, we know that the directional derivative is nothing but the gradient inner product the direction. So here we will so some lambda d limit lambda tends to 0 or lambda k if you want also xk. This is nothing but, so this is a directional derivative. We just write lambda this way also if you want. Here we usually choose lambda greater than 0, that is why I wrote lambda down arrow 0. So this is what I already have said to be strictly greater than 0. Then by the definition of the limit, limit means that at the tail would lie in a neighborhood of the point at which the limit is converted, of the limit point, the tail of the sequence. So essentially it means that, but if it is equal to 0, you can't say anything like that. So it means that there exists lambda greater than 0 sufficiently small that is, as x k plus lambda d is very near x k, right, then so as the limit, so as lambda becomes smaller and smaller, because we are taking limit as lambda tends to 0, we will have f of, that is, so here is your value, the limit value, and here is your 0. So the limit, all the values cannot lie here, then the limit value would be greater than or equal to 0. For the limit value to be strictly greater than 0, it has to cross over 0 and come to the negative side. The limit value to be strictly less than 0, some points has to cross over to the negative side. That is the intuitive way to look at it, and if you do not go into the details. So there would be a lambda, whatever you want to say, lambda k if you want, or lambda dash, say lambda dash. This would simply imply and simply from here you can just write that this implies that this is nothing but strictly less than 0. So lambda dash I can now set as lambda k. Now, what is D? How would you choose a D? How would I choose a D that will give me this condition? How would I choose a D which will give me this condition? Okay. So, in order to do so, a very important idea is choose D to be, that is called the steepest descent method. I will only tell you about two unconstant methods. D is negative of the gradient at xk. So at xk you can actually choose a descent direction, dk in fact if you want, does not matter. You can write this as k also, but you choose d or dk if you want. The direction to move from the k the iterate. So you can choose to write it as dk. So if you want, you can put dk also here, does not matter, because I was just concentrating on just the point xk, so I did not specifically write dk. So because here I will have points x1, x2, x3, x4 like that. So here you have dk. So what is grad fxk dk? This is nothing but grad of fxk minus grad of fxk. And this simply means the minus of the inner product of this with the inner product of this, which is nothing but norm of grad fxk square. Now, grad fxk is not 0, so its length of that vector cannot be 0. So, unless it is a 0 vector, no vector can have length 0, and there is a negative sign here, it is positive. So, this is 0, strictly less than 0. So, this is one thing that you have to keep in mind. This is one of the most popular methods to actually describe what is the meaning of a descent method, but it does not mean that that is the only form of descent method you have for unconstant problems. So, these type of algorithms, so that we generate in this form is called the descent algorithms or monotone algorithms, where the function values are going down. In many cases, for example, in convex optimization, we will be able to talk about non-monotone algorithms, means you really do not have to bother about whether the value is going up or going down, you really show that the sequence you generate actually hits the optimum, the actual solution. So suppose I choose my dk in the following way. And now suppose the function is twice continuously differentiable, it is a Hessian matrix which is also continuous, and a Hessian matrix which has invertible, which is also invertible at every point. Suppose, so I will choose, so here is the Hessian matrix, once I choose this, what you get is, so here also you will similarly you can show that this is strictly less than 0. So grad fxk into dk is nothing but minus grad fxk grad square fxk inverse grad fxk. Now, suppose I assume that the matrix grad square fxk is positive definite. So, I am considering a class of functions called strictly convex functions. I will urge you to read it from the net, strictly convex functions. So, I am just taking this, here there is a grad fxk, it is getting hidden by the board, here there is a grad fxk. So, if the matrix grad square fxk is itself positive definite, its inverse is also positive definite, and every positive definite matrix is invertible and its inverse is also positive definite. So, with any grad fxk non-zero, a positive definite matrix always has the inner product to be strictly bigger than 0, and with a minus sign here I can write this to be strictly lesser than 0. So, when you put this, so the Newton method simply has an form like this, xk plus 1 is equal to xk minus xk plus dk, basically lambda is 1, that is called the pure Newton method, inverse of this matrix into grad fxk. So, this will give you what is the Newton's method. So, all these results have convergence analysis, that is, given the method you should be able to tell what condition on the problem data on the function, or what should be the nature of the gradient, that would actually allow you to say that when I have a chain of iterates, these iterates are actually taking me towards solution. So, if you stop at a very high value of k, then you are making sense, you are actually making sense because you are progressing towards optimum. So, that's a very important thing. So, I will now come to a much more advanced topic, because as John told me that I should really tell you more about convex optimization, because he is also going to concentrate on convexity. So, that is what is really takes place in practice. So, very recently it has been observed a large class of application problems, specifically in engineering, is of this particular form, where you want to minimize the sum of two convex functions. See, minimizing convex functions is a different game, because it has much more power, because every local minima is global, it has nice tools, it has many good behavior, so it has a lot of power. So, the thing that you are doing here with minimal amount of information of just differentiability can now be resolved with more information that you have about convexity. So, here basically you do not have to bother much about these sort of things, that what I have written here, proper, lower continuous, semi-continuous functions, etc., etc. You just think that you have a situation where you minimize a function f(x) plus a function g(x), where both of them are convex and one of them is differentiable. See, convex differentiable at all points of the domain, right. Of course, they must have the same domain, right, otherwise they can't, you can just say it is on Rn basically, does not matter. So, these sort of problems were first realized to be important in signal processing. So, they were very, very important. So, how do you solve a problem like this, where one part has differentiability information, other part has no differentiability information, and that is exactly the type of methods. So, for them, these methods that are developed are called the proximal gradient methods, and that is what we are going to discuss at certain length. See, every basic convex optimization problem is also a special case of that method, because if you put gx equal to 0, then you get this problem, where f is any convex function subject to x element of C, which may be differentiable or not differentiable. Sometimes what happens is that, given a convex problem, it is much better to solve it as a regularized problem, that is, you solve it as a, you approximate the problem and you solve a sequence of approximate problems, and look at where the solution of the sequence of approximate problem goes. Now, there is a class of functions called strongly convex functions. So, how do you create strongly convex functions? So, take a rho greater than or equal to 0, okay, and construct a function f(x), which is a sum of gx plus rho times, or rho by 2 if you want, rho by 2 is better because you can differentiate. Norm of x square is anyway a convex function. So, if you add with any convex function a term like this, the resulting function is called a strongly convex function. It does not matter whether g is differentiable or non-differentiable. Do not confuse it with this f and g. So, this then f is called strongly convex. If you want, I can change the name. I can put this as h and I can put this as, say, psi, right. So, then psi is called strongly convex. So, what is the property of a strongly convex function? A strongly convex function over, if you want to minimize it over any closed set, closed convex set, it will always have a minimizer. Minimizer will exist and it will be unique. This uniqueness is a very, very important thing. So if you have a convex, if you just have a convex problem, which is not a strongly convex one, unique minimizer is not guaranteed. Right? If you have a convex function which looks like this, and I will give a concrete example of that. So the solution set of this problem, the minimizer of this problem is this, all these points. There is a type of function called distance function which measures, we have already talked about in the projection, measures the distance between a set and a point. So given a point outside C, so you are measuring. So when x is in C, the answer is 0. So this is a convex function. When C is convex, dCx is a convex function. This is called the distance of a point from a set C. Now what happens is the following, that if you look at this as a one-dimensional thing, so you would take a set here, say 0, 1, and you want to compute the distance function. So if you take any point here, the distance is 0. If you are in the set, then the distance function is 0. Otherwise, the distance function is positive. So the moment you move away from 1, as you go further and further away from 1, the distance between this point and the set, that is the length of the projection, increases. The same thing. So here the minimizers, set of minimizers of the distance function is the set C, because the minimizer, because the distance function is always greater than or equal to 0, and over the set C it is equal to 0. So the minimizers are lying at the set C, which is infinite. So for a given convex problem, you cannot have infinite solution, but if you have a strongly convex problem, you have a unique solution. Here is a paradigm shift that we really have to take care of, because so what happens when you have a convex problem, in many practice they add along with it a strongly convex function. When you add a convex function with a strongly convex function, it becomes a strongly convex function, and hence you will have a unique minimizer. So this sort of thing is very, very common, this or this, whatever. So with epsilon k you add gx, epsilon k is a positive number which is going towards 0. So this is a strongly convex function, and you add, you get a strongly convex function. So for each k, you start getting a unique minimizer. So when you look at which limit it is going. So that's the whole thing. So the limit, because C is a closed set, the limit would remain in C, because of the C is a closed set, and the solution so the limit finally will solve the actual original problem. So you are now in an easier state, that the sequence of approximate problems that you solve give you unique solution, and this is the power of convexity. It is not possible in any other situation. That is the power of strong convexity. Actually, strong convexity is the most important class. So here I have emphasized this. So this kind of regularization was actually called Tikhonov regularization. So here I will tell a story, because I met a student of Tikhonov, and there is somebody called Alexander Stochastic in Russia, in what is the place? Forgetting the place. It's near Siberia. So I was in a conference, in an international conference which was held in Mongolia. So Stochastic came, and the conference organizer was his student. He was a Mongolian big shot in optimization. He's a powerful guy, a very good man, of course. So he was going after his teacher, teacher, can you tell me this? They still have that respect. They don't call, Arey, professor this, they say teacher. It seems Russia, when you are, somebody has taught you, you're a PhD supervisor, you have to address him as teacher all your life. That is what they're. So one day I was going around with Stochastic in this, there's a lovely square in Ulaanbaatar called the Square of the Revolution. So he was talking about all these things, and Tikhonov, we were discussing Tikhonov regularization. Stochastic does a very difficult problem. He wants to look at maximization of convex functions. Maximization of a convex function is very difficult. Actually it's a non-convex problem. So he was telling that, okay, my teacher is academician Andrei Mikhailovich Tikhonov. Oh God. So what Russians are very different. The stories you are hearing about Danzig and US, which is very inspirational, Russians are regimental. So I give you this problem, you solve it. I also have those experiences. I worked with Russian mathematicians. So I give you the problem, you solve it, and then you think. Well, just to tell you a little bit of the story, when I was a postdoc student in Barcelona, I shared a room with a very famous Russian mathematician, now passed away, called Alexander Mikhailovich Rubinov. So A.M. Rubinov. So I had to sit there. So I had just gone. So I was more interested to go and see Barcelona city rather than sitting and thinking. I had some problem in my mind, but okay, I was not thinking fresh, new. So it was around 3 p.m. and I was a bit, I was feeling a bit restless. I should go out to see the city. So he came and asked me, what are you doing? I said, I want to go to the city. I'm not thinking much on something. Okay, you can see is always there, but research has to progress. So I give you my book. I give you my book, I give you the problem. This is the idea, you try to solve the problem. Solve the problem, if the problem solution is good, I write a paper with you. So my city going was, so you read it and we live in the same block in the apartment. So in the evening you come to my house for a cup of tea, for dinner, and then we discuss you have any problems. So he means that from 3 p.m. I should now study and to go to his house at 8 p.m. and then ask all the difficulties I have. I understood that I had no choice. So I really went down and really studied and went and asked him and then worked on the problem for 2 months, and it was a bit complex because you had to learn a lot of things. It's something called abstract convexity. It's something parallel to convex analysis on very special class of non-convex functions, increasing functions, functions which are increasing. So on certain parts of the domain. So it's called monotonic analysis. So, but this problem was on Hadamard, the Hermite Hadamard inequality. There's a famous inequality, integral a to b fx dx if f is convex is less than f of a plus f of b by 2. So if I don't have f to be convex, but I have f to be quasi-convex, then what is the inequality? And how do you find the constant of the inequality, the bound and all those things? And there was a specific problem to demonstrate. So then after two months, I went to him with the results. So in between, I discussed a bit. So, but anyway, I went to Barcelona too. My actual postdoc guide was very, very worried. One day he came at 5 o'clock. He was Spanish. He came and said, "It's Friday, 5 o'clock. Joydeep, you're still sitting and working. Come on, everybody has gone. I'm also going home. Come on. But luckily, Rubina was not there that day. So, but he was very enthusiastic. So when I gave the paper to him, he said, "Now you go. You come after 2 hours. Then we discuss." So I was going and doing something in the computer lab. It's called Sala de Ordenadores in Spanish. So then I met his wife Zari. He said, "Okay, Joydeep, if he says he writes a paper with you, your career is made. And if he doesn't, I am sorry. So I go after 2 hours, and then I ask him, okay, it's very nice if we write a paper. Then he started becoming friendly and discuss. He said, I don't like Kuntakar condition. What is this Kuntakar condition? Two convex sets have no intersection. That is the meaning of optimality. You separate a separating hyperplane. That is all. So you get the condition. What is this? So Russians have a very different way of looking at the things. Very, very different way. When you really, they mean work. It's not like inspirational like America. Oh, guy, you try out, enjoy yourself, have a beer and go to the party and think of it. You just sit down and work, quite like us basically, the socialist pattern. So, but you know, he was very inspirational, very, he will tell a story. There was a guy called Kutataladze in Russia, he's still alive, and Alex would always say, you know, Kutataladze worked very much in convex analysis and algorithms, all those things. And Kutataladze and his wife would say, Kutataladze is a very bad man. Alex is a very bad man. He said, no, he's my friend. How can he be a bad man? Well, no, he's a very bad man. And I remember, you remember that in the last class I talked about the Rockefeller-Shenichny condition at the end. So Shenichny was a Russian mathematician. So one day when I was there, there was a he was very sad. Alex, what happened? Oh, my friend Shenichny has died. He has died? Yes, he took a lot of vodka and he died. so that's a part of the Russian story. But you know, the Russian school called this algorithms in convex optimization was first built by a Russian school in Kiev, led by Noam Jeshor. And a lot of modern developments in convex optimization are due to the ideas which came out of that Kiev school of convex optimization. Yes, that is that. We have a paper in JMA. It's true. True, and we got a very sharp bound basically. The inequality, that modulus of the inequality was sharp. But lately there was, sorry, I just forgot to put this. There is a class of problems where, you know, especially these come out in image processing, where you don't really attach a strongly convex function, but you attach a function which is convex again. So you can say, oh, you are making a complex problem more complex. No, but such functions, when you attach such functions, their solutions can be achieved by something called exact penalization, and these type of functions, usually there are some class of norm functions, the L1 norm. They actually give you sparse solutions, and sparse solutions are used in sensing, compressed sensing. So this is a very these structures are very important in absolutely. These structures that you saw are absolutely at the frontier of knowledge, absolutely research at this moment, right? So now this is L1 norm. L1 norm is the max of norm of x1, x2, norm, those things. So this one, what does it say? That give me, I want to solve the equation, linear system of equation Ax equal to b. And these are system of equations you use in economics, in engineering, in many places, Ax equal to b. So when you solve Ax equal to b, I want a solution which has sparse solution, means most of the entries are 0, very few entries are non-zero. So it has been observed that this can be achieved by actually setting it up as an optimization problem, a convex optimization problem. Now how do I, but the problem again is, how do I solve this problem? Because again it's a non-smooth problem and things can be difficult. Anyway, and it's again you have constraints to handle, and so the idea in optimization algorithms has always been to transform a constraint problem into an unconstrained one. Penalty function method or barrier function method specifically for convex optimization and interior point problems. This is exactly that technique, that you move from a constraint structure to a unconstrained structure. So, in this case, this problem can be solved by writing this problem as this, because finding a solution of Ax equal to b means what? Ax minus b is equal to 0, this vector. So, norm square of Ax minus b is 0. So, if you minimize, norm square of Ax minus b whole square is greater than or equal to 0. So, if you minimize and find an x which gives you equal to 0, that is the solution, right. So, basically this is called the least square minimization problem. If you forget this and I just want to solve this, so solving a system of linear equation is actually can be shown to be equivalent to this problem, this optimization problem. It is called the linear least square problems, and it is applied in many places till date. Even the latest book called Optimization Models, which I will try to get not for this class, but for the next tutorial class. Next tutorial class is when? Tomorrow. After next tomorrow. So, that is the last tutorial class, I guess, or one more. Okay. So, that I will show you that there is absolutely a latest book on optimization models has a huge emphasis on this linear least square, these least square problems. So, then if you want to have this A norm, you actually add this function. So, here we are essentially going in the method of Seng and Friedlander and Paul Seng. Paul Seng was a wonderful mathematician. He was a student of Dmitry Bortsekas from MIT, and he was working at Washington, Seattle, where Rockefeller, the greatest guy in this area, is from. So, he goes to China, and he is very fond of KKing, this river KKing. He started river KKing in the Yangtze River. What is the full name of that river? Very famous, Yangtze River, Yangtze Kiang. And then he vanished, never came back. It's just in 2010 or 2011. He simply vanished, and nobody till date knows where he is. I mean, has he been just taken off, or he has gone somewhere, vanished? So, no. See, a subject when you especially a lecture is not interesting unless you tell a bit of stories associated with the subject. Yeah. Life is all about fictions, boss. Don't worry about it. See, if you, so what does it show? That if you actually have an xk going to x star and mu k going to 0, then x star actually solves this problem. But this is sometimes called the lasso problem. That is also used in imaging, basically. And this penalization, this is called exact penalization. That is, there would be a mu k for which the solution of this problem is the solution of this problem. That is called exact penalization. This is called penalization. Either I penalize the constraint or I penalize the objective. So, here I have said that solving Ax equal to b is same as solving this, and then I do the penalization by writing this. So, this is an exact penalization means that there will be a mu k for which the solution xk of this problem would be a solution of this problem. So, the Friedlander and Seng's paper is actually very important, specifically in modern applications, to really show that such things can happen when you choose a very proper convex function as your penalty term. So, here we have written that is there is another interesting type of example. So, this is it's called just a moment. This is called a robust principal component analysis. This a problem is called the robust principal component analysis, and let us see what it means. So, you have a m cross n matrix which has some data. In principal component analysis, the idea is that you want to express, you want to decompose the matrix into two parts. One part is a low rank matrix and one part is a sparse matrix. The idea of doing this can be achieved by solving this problem. Now, please be careful, here my variables are no longer x element of Rn, but my variables are matrices. And this norm that you see, norm x1, is a summation mod Aij of all the elements in the matrix, and this norm z star denotes the nuclear norm. So, this nuclear norm has now become quite popular when this Immanuel Candace applied it to matrix completion problems. There is a matrix where some data is there and some data is not there. So, how to put in those data back, how to fill those empty places. So, this is very important in medical imaging actually. When you have this, you have some data which some parameters are not clear. So, how do you get them back? So, this nuclear norm is a sum of the singular values of the matrix Z. Given a matrix Z, so the sum of the singular values of the matrix Z is the I assume that you know what is singular value decomposition. If you do not know, just forget it, take it as an example. Okay. So, in your mind, what is the crude thing that you have done? You have decomposed the matrix into A minus x and x. So, A minus x is the low rank matrix, that is, this R is actually the rank of the matrix. That is why we have trying to compute the nuclear norm, because nuclear norm is actually depending on R. So, if you minimize the nuclear norm, then this value also has to be small, and as a result this R has to be small. If R is big, then it will be big. So, more the R, the more singular values there are, and so if the rank is small, so this nuclear norm would be small. So, if you minimize it, and you get what you call a small rank matrix. So, the idea in your mind intuitively is to break it up like this. So, this is your small rank matrix, and this is a sparse matrix, because if you minimize the norm, the one norm, you actually get sparse solution. So, sparsity is introduced by this one norm. So, let us start trying to build up. You see, the premise of building of models, optimization models, in the sense that solution techniques for convex optimization, you will see is very different from what we have just written about these descent methods. So, there are many descent methods, trust region method, conjugate gradient method for the specific problem, quasi Newton methods, and these and that and that. There are a lot, but from the convex, once you take convex optimization problem, there is something, it's done in a different way. See, the key idea always is this: you have a convex problem, add a strongly convex problem to it, function to it, make it strongly convex, solve it, bring down the parameter epsilon, make it lower, again solve it, make it lower in steps and again solve it. That is the key idea. So, you are not really bothering to check at every xk what is the functional value of the original problem, what is the functional value of the objective. So, that is not checked. So, there is a definition of the proximal map of a given convex function x. So, this is something called inf convolution of two convex functions, but we will not at all get into the issues of inconvolution. That is a very advanced topic, we do not do. So, here what you do, what is the meaning of this proximal map of a convex function h computed at x? It means if h is a given convex function, consider the fixed, because x is fixed, I want to compute it at x. So, if I want to compute the whole thing at x, then it is arg mean of, so you construct a function, construct new function hz plus half norm z minus x square, x is a fixed number. Now, hz is convex, but the square of the norm is a strongly convex function. And if you add this, a strongly convex function to a convex function, you get a strongly convex function. So, for does not matter this function, whatever be your x, if you fix the x, this is a unique minimizer. So, that value of that minimizer, that hz is the value of this function, right. Now, let us look at more at the optimality conditions, how optimality conditions relate us to. So, I know that suppose x star is the unique solution of this z star, not x star, z star is the unique solution of this problem. So, then proximal mapping is nothing but z star. Prox h, I have written, I think that bracket, curly bracket is not required. So, it is prox of h computed at x is z star. Obviously, it depends on the choice of x. If you change the x, the z star will change. So, which means 0 must belong to the subdifferential of this function evaluated at z star. You must observe that this function absolutely is an x dependent function. If you change the x, the structure of the function is changed. So, at every x, when you want to compute the proximal map, you are solving a strongly convex, you are minimizing a strongly convex optimization problem. And there are nowadays very standard routines for that. You can even put into the MATLAB's as an optimization toolbox, if you put it will solve it. So, now this means, now I will apply the sum rule, but you know when the subdifferential of a convex function, if your function is differentiable at a given point, the subdifferential has only one entry, that is the derivative. That we have already mentioned in our classes, that when if a convex function is differentiable at a given point, the subdifferential at that point has just one element, that is the gradient. So, in this case, we will just have the gradient. So, it will be 0 element of del h z star plus z star minus x. Assuming that these are all finite convex functions, so all the properties that we were talking about, they all hold and the sum rule can be applied. So, x can be now taken to the other side. So, x element of del h plus I z star, we can combine them. So, z star, so this is what is called a set valued mapping. So, del h x star is not just a point, del h x star is a set. So, del h plus I z star is a set. So, x element of this means z star is an element of the inverse mapping of this map applied at x. But that inverse mapping also has to be set valued. It will take a point to a set, it cannot take a point to a point. But it was been shown by Minty, who by the way was an electrical engineer, is because he needed for studying electrical networks, that this mapping is actually single valued. Though this mapping is set valued, that here this mapping is taking this z star to a set, but when you want to find a inverse of this, that is z star is actually equal to this of x. So, what is that z star? How do you compute it? See, we have not really computed z star. We said that there is a z star which will exist, and so we are trying to now compute the z star. So, here what happens is that z star is the element of this, but this is single valued actually. So, because this is called the Minty's lemma, and then we can write z star is exactly equal to this. So, this is a single valued mapping, and this is one of the most wondrous results of modern convex analysis, that this which looks absolutely set valued, its inverse is a single valued map. Del H plus I is a set valued map, because H I do not know, I have not put any differentiability assumption on that. So, it is called the resolvent of a monotone operator. Now, let us consider H to be the indicator function, which you already know, that it is 0 when x is in C and is plus infinity when x is not in C. And then let us try to compute the proximal map of this. So, if I try to compute the proximal map of this, what would happen? This will happen. This will happen. So what will happen is del C x plus half z minus x whole square. So, when z is x is in C, sorry, when it will be z, this will be z here. This del C x that you see here is a z. So, these are z, it is not x. So, when z is in C, this is 0, but when z is not in C, it is plus infinity. So, plus infinity is not a part of the minimum thing. So, basically this problem, which looks very unconstant one, can now be brought into a constant structure. So, for all z equivalent of C, this is 0, and so we will have this. But what is this? This is nothing but the projection mapping, the projection solution. A solution of this thing is nothing but the projection, because you are basically computing the square of the distance of the point x from the set C. So, this is nothing but the projection. So, the proximal mapping of the indicator function is the projection mapping of the set C. The proximal mapping of the indicator function of the set of a closed convex set C is the projection mapping of the closed convex set C. So, the convex analysis has a lot of these symmetric and very beautiful links, and that makes it interesting. So, usually, see, when it comes to algorithms and when you want to implement it, there are two different things. Implementing algorithms is one thing, and writing down convergence analysis is another thing, with all stories you can invent and all conditions you can invent. But at the end, when you want to write a convergence analysis, you should be able to keep in mind what you cannot do and what you can do. So, in optimization algorithms, it is profoundly important to know what I cannot do, rather than trying to know what I can do. You can do this, but it is very important to know at the very outset what I cannot do. If you think that, okay, theek hai, to likh diya, so I can do anything, you can't do anything. So, this beautiful theory and theoretical edifice and beautiful algorithmic structure all has a lot of limitations behind it, and unless you appreciate that limitation, hardly you would really move. So, for example, here I have G is convex and differentiable, and take F to be strongly convex, doesn't matter. C is Rn. This is one of the one setup where you can do something. A proper lower continuous, just forget it. You just think it is continuous. So, G is convex and F is convex. Dome G is Rn means it is on Rn to R, this is all Rn, and C is Rn. And it is a setup, and you have to also guarantee that I will only consider functions F. The F must be such that the prox of F must be easily, prox function which we have just discussed, the proximal mapping must be easily computed. This is a very tricky term, what is easily computed. So, basically once you say that, you limit your F's. So, only when I have that structure, then I can handle this problem. So, that is why somebody was asking me that can an algorithm work for all problems. So, it cannot work for all problems. So, there is always a limitation, right. So, this is something. So, and then where F could be a continuous convex function and G is a differentiable convex function, that is all. So, this thing, this one, last one, is absolutely recent research. It has come out in 2016 or 2017, 2017. Bauschke's paper, Amir Beck and Bauschke's. So this is absolutely recent research. People were actually concentrating up to this 2. So this is absolutely recent research. For case 1 and case 2, you assume that G is globally Lipschitz with Lipschitz constant L. So what is the meaning of G function being globally Lipschitz? It simply means that for any xy, so there exists a k greater than 0 such that for any xy in Rn, g of x minus g of y is less than equal to k times norm of x minus y. The distance between the functional values at x and y is less than some constant into the distance between x and y. So there is a control. So this is called Lipschitzian property. So this has to hold for all x, y. I will show you an example. Suppose gx is a convex or a quadratic function, right? Half x mx. Okay, no, I will show it later. So, but this condition is not so easy to actually hold. No, I think there's some mistake here. Just let me check it out. Grad G is locally Lipschitz. I don't think it is G is locally, it is called grad G is locally Lipschitz. So if G is locally Lipschitz, see, convex functions are locally Lipschitz in any way, but G, this is just a moment. Maybe I made a mistake. The gradient of G is globally Lipschitz. So gradient is not the, that's exactly what I am trying to think. It's not the function, because every convex function is locally Lipschitz. It's very difficult to get them to be globally Lipschitz. So it's the norm of gy minus gx. So norm is in Rn, Euclidean norm. So this has to be true. So an example for this would be true. So this is a gradient. This is say y minus x. So if you take gy or gx to be half of x mx plus qx, so quadratic function, and the gradient of gx is mx plus q. Right, then if you put here mx plus q, I think it's very difficult to find examples other than this. Largely it is looking at for quadratic functions. So my plus q minus mx minus q less than equal to, so what is happening? This is equal to norm of my minus mx, and this by simply what is by the property of the norm is this. So this is your L or K, whatever. It is called the constant, Lipschitzian constant of Lipschitzianness. So this constant has to work for all y and x. So this is an example where it works. It works for some other examples also, but it's not so easy. So that this has to be gradient of g. G cannot be globally Lipschitz. The convex differentiable function is hardly globally Lipschitz. It's always locally Lipschitz. Locally Lipschitz means at every point around the neighborhood, the Lipschitzian property will hold with some k. If you change the point, the constant will change. Here you are expecting at every point the constant is same. जो भी point में ले जाओ constant same है. Then it is called globally Lipschitz. So, it is a gradient which has to be like that. So, before we proceed, we observe a little bit of this is just a little bit of chunk of handling things. So, instead of having the prox function of h, I am having the prox function of lambda h, but that same prox function of lambda h can be rewritten in this form basically, with the lambda being attached to the strongly convex function finally, that is all, nothing else. You can see it in the notes in detail. अरे कहाँ चला गया? So, when C is equal to Rn, one of the first steps to take is this. So, you see in the case 1, F is convex and strongly convex, that has been told. Now, what we are, so these are strongly convex problem. So, what you are doing, you are minimizing, so x is given, x is fixed, so x is your current iterate. How you go to the next iterate? So, you go to the next iterate by solving another convex optimization problem. So, gx is fixed, gx u minus x, this is x is always fixed. So, this is an affine function. This is a strongly convex function and this is anyway given to be strongly convex. So, if you do these calculations, so x plus would finally come out to be, I am not going into the details of the calculation. So, the next proximal, next iterate, x is the current iterate, xk possibly, x plus is xk plus 1, it is exactly the proximal mapping of x minus lambda grad gx. See, we have done some interesting things. So, you must hear f vanish हो गया यहाँ से, नहीं vanish नहीं हुआ, f यहाँ पे hidden है. Because this is what you have to do at the end, which we have very cleverly written like this, because it looks nice and compact. So, this is the key iteration step basically. So, this is the key iteration step. So, this is the algorithmic structure of the proximal method, right? Proximal gradient algorithm. So, you can do some more manipulations with that, and you can write, for example, so basically what you are writing, xk plus 1 is prox f lambda k, lambda f xk minus lambda grad gxk. So, instead of x plus and x, I am now writing xk and xk plus 1. So, you can, if you write g lambda x is like this, you can write xk plus 1 finally as xk minus lambda g lambda x. This is exactly what we had done in the descent method. Xk plus 1 is xk plus lambda of plus lambda k dk. So, dk if it is minus grad f xk, it will be xk plus 1 is xk minus lambda grad f xk in the steepest descent method. In the steepest descent method, what should be the iteration step? In the steepest descent method, the iteration step is xk plus 1 is equal to xk minus lambda k grad f xk. This somehow looks like the steepest descent method. So, something which had got nothing to do with the steepest descent method, nothing was mentioned, we have brought it into a scenario where it looks like as if it is the steepest descent method, where g lambda is some sort of a gradient. Because it behaves like that, it is called the pseudo gradient associated with the convex function. So, it is a pseudo gradient, right. So, now you look at the formal algorithm which we are going to discuss. This algorithm given in this this guy Calafiore and Elgoi. So, G is convex and differentiable on Rn with Lipschitz continuous gradient. So, gradient was Lipschitz continuous and G is bounded below on Rn. So, these are the, and F is anyway assumed to be strongly convex. So, we have to observe a point. So, when lambda gx is equal to, so x star is an optimal if and only if lambda gx star is equal to 0 in this case. So, it is exactly operating as if it is a convex optimization problem. That is why it is called a g lambda is called a pseudo gradient, though it is really not a gradient. So, I am not getting into the details of the computation. You have to look into the computations very carefully, but please understand this is absolutely knowledge at the frontier of the subject. So, if x minimizes f plus g over Rn, then reversing the, so x star minimizes f plus g over Rn if and only if g lambda x star is equal to 0. So, g lambda x star somehow encapsulates as if it is a gradient of both f plus g, even though one part f does not have a gradient possibly. So, g lambda x is, you see, if g lambda x is equal to 0. So, g lambda x is sometimes referred to as a pseudo gradient. The key assumption is that grad g is Lipschitz continuous, which is exactly what I wrote that. So, once you have that g being Lipschitz continuous, you can show that this following relation gy less than gx plus this actually holds this relationship. And these are very key relationship which we have to use. So, we did some more manipulations. It would look like manipulations only. So, what happens is that this function, you can always show that a class, you can always create another class of convex function generated out from all these discussions. We will not get into all the technicalities because people might not be so involved with the technicalities. So, again you are trying to rewrite this fact and you are trying to rewrite. So, and so this is quadratic approximation, and so there are several things that you are using. You are using the gradient is Lipschitz, and so what you see, all these things done because what we want to show at the end that the proximal gradient method, though it does not look like a descent method, can actually be shown to be a descent method. By using this pseudo gradient, I can show that what I am getting, that f of xk plus gk is strictly bigger than f of xk plus 1 plus g of xk plus 1. So, I have actually decreased the value. So, all these calculations finally show that your objective function, you are actually, this proximal gradient method is also a descent method. So, here again you will use strong convexity of AF and all those things, and so there is so there are several things that are used. So, I am not getting into the details of why this happens, and so the fact that G is strongly convex and has a Lipschitz continuous gradient. So, here we are coming with the fact that f is a convex function which need not be differentiable, G is a differentiable convex function which is strongly convex and has a Lipschitz continuous gradient, right. Because if you say take G to be this with M positive definite, then it becomes a strongly convex function. So, here there are certain relationships that we want to establish, and basically we want to now show that x, the thing that we generate xk actually takes us to the solution. That has been our aim. So, that is at the end what we are going to try to show is that a relationship like this, that x naught is the starting variable, xk is the current variable. This is a number less than 1, because L has been showed to be bigger than rho. If you go to the previous slide, you will observe one of the things that we showed, somewhere we have showed that L is bigger than rho, right? L is bigger than rho. So, once you have this, and then when you ultimately derive a condition like this, so this is a number less than 1. So, as k tends to infinity, what is happening? This is going to 0. So, this is a fixed number, x naught is fixed and x star is, because we have assumed there is a solution. See, we have to go on with the assumption there is a solution. So, there is a solution. So, if there is no solution, there is no use writing algorithm. So, x naught minus x star, this part is a constant. So, this goes to 0. So, what happens? Xk minus x star whole square is less than or equal to 0 as k tends to infinity. So, which means, but this is anyway always greater than or equal to 0, which means as limit as k tends to infinity, xk minus x star is going to 0. So, xk is going to x star, and that is exactly what we had set out to prove. And that is it. And there are some other issues also which I am not getting into details with you. Is that this is a, again, you know, here we talk about Lipschitz, and then we say that we drop the Lipschitzian assumption and see whether we can get the same thing with the Lipschitzness on grad G and strongly convexity on grad G on G, that is dropped away, and then we see whether we can get the same condition. So, that is just an addition. So, we are not getting into that. So, this is the basic idea. So, what I wanted to explain to you is the basic idea, how do we proceed, that you know, that's why did I talk about descent methods at the beginning, is that at the end even a method which does not look like a descent method can be shown to be a descent method. Because descent methods are much more methods which generate confidence that yes, I am actually going down. See, why people use Newton's method even for non-convex problems? Because somehow they manage to make at every k xk grad f square f xk positive definite. But this is not always true, it is not possible. So, that is why quasi-Newton methods were developed. So, if they replace grad f xk by some approximate matrix called hk, which were positive definite at every k, and they were successfully applied to non-convex problem because they were descent methods. I know my functional value is always going down, maybe I will going towards the local minima, my function value is going down, it is not going up. So, I am not getting a very high value, maximization value, I am getting a minimization value. So, this is so what I have just taught you and what I told you is very basic initially. What I have taught you is absolutely at the frontier. So, we just jump from 0 to 10 sort of. So, you can read the notes which will be uploaded in the things. Now, you can have access to the notes later on also, so no problem. So, my lecture is over and all my lectures are finished. So, this is the last lecture. So, anything that you want to ask now. We have 10 minutes to go. So, your time starts now. The rank, it can be shown that it minimizes the rank. It's because these are, so rank minimization is actually a non-convex problem. You want to minimize rank of a matrix. Rank of a matrix is a non-convex function. So, by bringing it into this singular, this norm, you bring it into a more of a convex structure. No, number of singular values must be equal to the number of equal to the rank. You are talking about the value of the See, they are trying to find an x which will minimize that nuclear norm, right. So, among all other x's, that norm is the minimum, right. So, when you have a minus some other x, the rank can change. Now, if this has to be the minimum, the rank cannot be very high. So, the rank is what? The full row rank. Rank is what? M can be the maximum rank here. Rank cannot be more than M, right? M is the rank here. Now, the problem is that it can be shown actually, but it's not a thing that can be done here, it needs a lot of machinery. That if you minimize the nuclear norm, that the x that you get, then you have a minus x part, a minus x star, that x that you get, you can minimize that. So, that rank, that would, that x, the minimization, any x which minimizes the nuclear norm a minus x, will generate the matrix a minus x with the minimum rank. It can be shown that rank would be minimum. See, a minus x, see what is x? X is also an m cross n matrix. Maybe sparse matrix, in reality sparse matrix, but a minus x. So, some values of a is changed, other values are not changed. This is also matrix completion, you see. Some lot of values are not changed because these are 0, and some values are changed. So, what they were telling that if you can, no, it is not very clear, but actually it can be shown that if you tweak a bit of these a values, basically a minus x, then you can generate a matrix which, you can generate a matrix of norm which can be which is less. So, there can be an x, a sparse matrix, which when subtracted, when a is subtracted from a, x is subtracted from a, will give you a matrix whose norm, whose rank among all other a minus x forms with other x's, sparse matrices, would be the minimum. That is what is the meaning. The rank of such a matrix would be the minimum. That can be shown. So, that is the low rank matrix. So, minimizing norm 1, so minimizer, how can you think of it? How can you think of it, norm x? When I say minimum of norm x1, I said minimum of the sum. So, the sum has to be minimum. So, now their item is fixed n. For norm x1, item is fixed. If the sum has to be minimum, it has to be sparse. Because if the sum it is not sparse, then the sum is not minimum. I can easily show that. But technically, you can say 0, 0, 0, 0, 0. But 0, 0, 0 will not come because you have added that a minus x star nuclear norm. That is why 0, 0, 0, 0 might not come just. But that x at the simultaneously is minimizing the nuclear norm as well as minimizing this norm. No, it has to be proved. There is a proof that there is a proof in the paper of Emmanuel Candice that this is actually this generates a minimum rank matrix. Because rank minimization is a non-convex problem. This is a difficult problem. So, they have to get this nuclear norm and do this sort of thing. Anything? Not given. Starting solution is anything you choose, whatever you think. After you take a drink of a coffee or Coca-Cola, you say that this is the starting solution. And Newton's method में थोड़ा ये रहना चाहिए, चौकन्ना. That you have to the convergence analysis says that you have to start from the starting solution should be near the actual solution. So, how do you, when you implement Newton's method, what do? You really see that okay, if it is not converging, After a certain number of iterations, you stop it, you change the iterate. Because who knows, I don't know the solution, so how I know that I will go near the solution or far away from the solution? It takes time. Implementation and theoretical analysis of algorithms are two different subjects. Implementation is a very different ball game, very different ball game. And this theoretical analysis and all the versions that we are giving are a different ball game. Oh, implementations are done by very different people. They always don't write algorithms. That's the whole point. So when you have, there is a team which works in optimization. There will be a theoretician, an algorithmic expert who generate algorithms, the theoretician will analyze the algorithm, and there will be a guy who will be implementing. These I have observed very carefully. Sven Lefier, for example, is an implementer. He knows how to implement it. And you know who was he working with, whose student he was? Roger Fletcher. Fletcher's algorithm, Fletcher's updating method for quasi-Newton method, BFG method and DFP method and all those things, David and Fletcher Powell method. So Powell is very famous actually for getting the, but you know, actually this quasi-Newton algorithm was already known to a guy called C.W. Davidon. He was a physicist working with the English Electric Company. So his thing remained as a note and it went over, nobody bothered about it. That you can replace the Hessian matrix with some approximation. So later on in 1991, when the first volume of Siam Journal of Optimization started, they had put it as the first paper. So C.W. Davidon then went to teaching and he didn't bother much about research. But the thing was actually sharpened computationally by Powell, MJD Powell, and in fact the highest award in optimization is called the Danzig Award in static optimization. And the first Danzig, it started in 82, and the first Danzig Award winners are MJD Powell and R.T. Rockefeller. So that's it.